Everybody, good morning, good afternoon, or good evening, depending on where you are. And it's my great pleasure to introduce our first speaker of today, Alexei Poltoratski from University of Wisconsin-Madison, who will give the first lecture of his mini course, and the first lecture is on inverse spectral problems for canonical Hamiltonian systems. Alex, please.
Thank you very much. And of course, I would like to thank the organizers of this program and this week for giving me this opportunity. And today I would like to talk about spectral problems for canonical Hamiltonian systems. So my plan is as follows. This mini course is gonna focus on applications of complex analysis to spectral and scattering problems for differential operators. And today and tomorrow, we will talk about canonical systems and the so-called Crane-de-Branche theory, which was designed to translate spectral problems for differential operators into the language of complex function theory. And the first two lectures will be based on joint work with Nikolai Makarov, and we will see how to solve some of the inverse spectral problems for differential operators using Toeplitz operators, inner functions, and things like that, which I assume many people in the audience know well and like. Now, the title of the mini course was Pointwise Convergence for the Scattering Problem or the Nonlinear Fourier Transform. And this will be the topic of the last talk on Thursday. And this will be one of the examples of a problem that you can find in this area. The scattering transform is very closely related to the spectral problems, and the nonlinear Fourier transform is practically the same thing as the scattering transform. And so in the last lecture, we will try to extend Carlisson's theorem on pointwise convergence for the Fourier transform to the nonlinear analog of the Fourier transform. So that's where the title of the whole mini course comes from. But to approach that third hour, we will need some preliminary work. And so today we will start with spectral problems. So as I already mentioned, this is all from our joint work with Nikolai Makarov, although at the beginning I'll just tell you the basic facts from the so-called Crane-de-Branche theory. So we will study the following system of differential equations. This is a 2x2 system. This is called a canonical system or canonical Hamiltonian system. So in this system, x is the unknown vector-valued function on an interval from t minus to t plus, a two-dimensional function. Omega is the symplectic matrix, the square root of -1 in the space of matrices. And really, any square root of -1, there are many of them in the space of 2x2 matrices, could be used in this theory in place of omega with some minor changes in statements and such. So H in this formula is a given 2x2 matrix, which is called the Hamiltonian of the system. So our requirements on H is that it's locally summable on the interval, and that it's greater or equal than 0. So it's non-negative definite. So we will see later in the course, and maybe tomorrow, that many standard second-order equations can be rewritten in this canonical form. This is really a very general form of a second order equation. And moreover, as Crane noticed many years ago, any self-adjoint operator with simple spectrum is equivalent to one of such systems in some sense, as I'm not going to specify today. Well, maybe I will. So if in this equation you apply H inverse to both sides, it becomes an eigenvalue equation for a certain operator. So H inverse times the right-hand side is going to be your operator. Of course, in this general setup, we do not require H to be invertible. So in general, if you multiply it by H inverse in the left-hand side, you'll have just a formal expression. But if this formal expression exists, it will define a certain self-adjoint operator. And so the statement that I just mentioned is that any self-adjoint operator with a simple spectrum is unitarily equivalent to this operator H inverse times this left-hand side for some choice of H. So this is really a very general problem that we are going to consider, and a very general model for self-adjoint operators. So in my talk, I will restrict myself to the case when the determinant of H is not equal to 0 almost everywhere. Just one second. So in the general theory, you don't have this restriction, and H is allowed to be non-invertible, like I said before, and vanish on some intervals and so on. In particular, a special case is when H has the so-called jump intervals, and those are intervals on which H is a constant matrix of rank 1. And if you want to study discrete difference equations within this theory, the Crane-de branch theory, then you have to allow those jump intervals. In fact, for a system of difference equations, they can be rewritten in this form with H consisting of only jump intervals. So we are not going to go into this direction and adopt this restriction, which outrules jump intervals, simply because this would make all the statements a bit shorter, and it will allow me to go over the basics of the theory faster. But in principle, you don't have to have this restriction. So if you agree that the determinant of H is not 0 almost everywhere, then you can renormalize the system with a change of variables and make it satisfy an even better condition that the determinant of H is 1 almost everywhere. And that's what we will do for the rest of our lecture today. So a bit of history. Crane was first to discover those systems that he called canonical, and he noticed all those properties that I mentioned, that many differential equations such as Schrödinger, Dirac systems, and so on can be rewritten in this form. And he also noticed that those systems produce some spaces of entire functions. And instead of solving spectral problems for those systems, you can look at uniqueness problems, try to describe zero sets and so forth in those spaces of entire functions. So a quick translation of spectral problems into the language of complex function theory. But he couldn't completely formalize the theory of those Hilbert spaces of entire functions that he obtained from canonical systems. So that was done a bit later by Louis de Branche, who wrote a book published in 1968 describing the theory of de Branche spaces of entire functions. They're now called de Branche spaces, and finishing the complex analytic part of the theory. So, unfortunately, back then, the founding fathers didn't produce a good text on the theory, and some parts of it exist in papers and some are missing proofs and so on and so forth. So the theory was more or less finished in the so-called regular case when the Hamiltonian is locally summable. De Branche, as I mentioned, wrote a book on that case, but there was no text containing both parts, the spectral part developed by Crane and the complex analytic part developed by de Branche. Right now, in recent years, such texts start to appear, and there is a book by Christian Remling that appeared recently. I should mention here that there was a chapter in the book by Dim and Mike Keane on the Crane-de Branche theory, but it was a short chapter and it only contained the basics. So, but now there are at least two texts that appeared in the last 7 years or so. One is a book by Christian Remling and one is a book by Roman Romanov. So the situation is improving, but still the theory is not completely finished. So let me continue. So now we will define the spaces of entire functions that I was talking about. So first of all, an entire function E is a function of the so-called Hermite-Biller class if its values in the upper half plane are strictly larger than its values in the lower half plane at the symmetric points by the absolute value. So for each z from C plus, we must have this inequality. And then with each Hermite-Biller function, you can associate a whole Hilbert space of entire functions. And they are defined in the following way. So B of E, the space of functions corresponding to the Hermite-Biller function E, consists of entire functions such that if you divide them by E, this ratio falls into the Hardy class H2 in the upper half plane. And if you reflect your function, so F sharp throughout my talks will stand for the Schwarz reflection with respect to the real axis. If you reflect your entire function and then divide it by E, then again this ratio should fall into H2 in the upper half plane. So that's the definition, the first definition of a de Branche space. We will have two equivalent definitions shortly. So with this definition, you can adapt the Hilbert structure from H2 in the space, and it becomes a Hilbert space. So the product in B of E is the product in H2 after you divide those two entire functions, and they become functions in H2, which if you write everything out, becomes this weighted L2 product with this weight. And so that's the inner product in the de Branche space. Let me quickly mention here that because the inequality here is strict, the function doesn't have any zeros in the upper half plane. So you can divide any entire function by this function, and at least this ratio will always be holomorphic. But for F to belong to the branch space, we needed this ratio to be in H2. All right, so that's the first definition of the branch space. And one of the most remarkable things about such spaces is that they admit a second axiomatic definition. So let B be Hilbert space of entire functions, any Hilbert space of entire functions. And suppose that it satisfies the following three very natural axioms. The first axiom is that if an entire function f is in B and it vanishes at a point lambda, then you can flip this lambda with respect to the real axis. You can exchange the zero for a zero at the complex conjugate point. So divide by z minus lambda, but multiply by z minus lambda bar. And this new function with this new zero must again belong to the space. So that's the first axiom. The second axiom is that all point evaluations at points outside of the real line are bounded linear functions. So actually, if this holds, then you can show that point evaluations on the real line are also bounded linear functionals, just using the closed graph theorem. But this way, when you consider only non-real points, this is a weaker restriction. So we formulate it in this way. And finally, the third axiom is that this Schwartz reflection with respect to the real line, which we defined on the previous slide, this iteration on entire functions, is an isometry in our space. Well, I forgot to read this part. So in the first axiom, when you flip a zero like this, it also should be an isometry. So, and the statement of this theorem is that if a Hilbert space of entire functions satisfies the three axioms, then it's a de-branch space for some Hermite-Biller function E. So it's really hard to come up with an example of a Hilbert space of entire functions that doesn't satisfy these three axioms. They are very natural. If the norm in your Hilbert space is evaluated on the real line, like for instance, the norm in the Pelle-Wiener space, then these three axioms will most likely be satisfied. And then the statement says that every such space is a de-branch space. Now, it's very common that you arrive at a Hilbert space of entire functions where you can easily verify these three axioms and conclude by this theorem that it's a de-branch space for some function E. And then the question becomes how to find this function E. And this problem is difficult in general and deep. And in some sense, it's an abstract analog of an inverse spectral problem, because the spectral information for a differential operator will give you a certain space satisfying the axioms, and then recovering the differential operator is equivalent to recovering this function E that generates this space. So hopefully we'll see this in my mini course later on. So how are those two objects related? The canonical systems studied by Crane that we defined in the beginning, and the de-branch spaces of entire functions that we've just defined on the previous two slides. So let's go back to a canonical system. And once again, this is a 2x2 system of this form. And let's suppose that we fixed a self-adjoint boundary condition at the left endpoint. Let's suppose for a second that T minus is finite. This will be our main case, by the way, that when T minus is a finite point. And let's fix a self-adjoint boundary condition at T minus and solve our equation. Now, since we are only fixing the boundary condition at one of the endpoints, the solution of the system will have a solution for every z. It will be a unique solution. This all follows from the general theorems about existence and uniqueness of solutions for differential equations. And so let's find this unique solution denoted by xz. Let's make the following entire function out of this solution. So now we fix t, and with this fixed t, we consider the following function of z. Z was the spectral parameter in our initial system. So the coordinate functions of our solution x become real and imaginary parts of E on the real line. Now, each of them is an entire function. It's not very difficult to prove, an entire function of Z. So with the fixed t, U is an entire function of Z, and V is an entire function of Z. Now, they're both real on the real lines, because if Z is real in this equation, then everything in the system is real and the solution is real. So we call such entire functions real entire functions. Those are the entire functions that are real on the real line. So both U and V are real entire functions. And E, written like this, is the general entire function given by this formula. So it turns out that this entire function for each fixed t from our domain of the system will be an Hermite-Biller entire function from which you can construct the branch space the way we defined it 2 slides ago. So now for each t from the interval where we consider our canonical system, we get our own, its own de-branch space. So this way we have a whole family of de-branch spaces for every t on the interval. So if you open the book by de-branch, that book from 1968 that I mentioned at the beginning, it's called Hilbert spaces of entire functions, where he defines these spaces of entire functions, gives the axiomatic definition, proves the equivalence of the two definitions, and so on, and goes on to study those spaces of entire functions, unfortunately without any connection to differential equations. So for many readers, that book looked completely unmotivated. But we know where those spaces come from. And in this slide, I will show you how they come, they appear in the theory of canonical systems. So in that same book, in the introduction, de Branch says that his goal is to generalize the theory of Pelle-Wiener spaces. And indeed, Pelle-Wiener spaces are de Branch spaces where the function E is the exponential function. You can easily check that they satisfy the axioms, and therefore by the second definition, they are de Branch spaces. And then if you just use E to be e to the power minus I AZ, where A is a positive constant, then our first definition of the branch space will produce the Pelle-Wiener space. So, but the Pelle-Wiener spaces are Fourier images of L2 on an interval. So if our new de Branch spaces are a generalization of the Pellewiner space, then they also must be a Fourier-like image of some L2 space. And indeed they are. And here we define the so-called Fourier-Weil transform, which is a lot like the Fourier transform, only instead of L2 on an interval, we consider L2 with the weight h. H is the Hamiltonian of the system. And this is a Hilbert space of two-dimensional vector functions, f1 and f2, where the inner product is defined like this. And here we must recall that H was a non-negative 2x2 matrix, so everything will be correctly defined here. It will be a true inner product because of that property. Now, our L2, of course, just like the usual L2, will consist of classes of functions. Here, remember that in general, H, the Hamiltonian H doesn't even have to be invertible at almost every point. And then when we apply it to this function, it may this vector may be zero. So we will identify those functions which H sends into zero functions. So once again, this is a space of classes of functions with this inner product. And then you can define the Weil-Titchmarsh transform with this formula. So in the usual Fourier transform, you, first of all, there is no weight. And second, you use the exponential function as the kernel. The exponential function is, of course, a solution to the simplest possible differential equation. And so you follow, just 1 second, you follow the same algorithm here, but instead of the exponential function, you use the solution to your differential equation, to the canonical system. And so in this formula, A and C are those U and V. I should have kept the notation from the previous slide. So AC is the solution to the canonical system, and you use it as a kernel in this transform. And you can define those de Branch spaces that we saw on the previous slide as the images under this Weil Fourier transform of L2 on the interval from 0 to t. Here we are, again, it's a slight misprint. So this, we are now considering the half-line, the system on the half-line from 0 to infinity. And then BT will be the image of this L2 from 0 to t. If I keep these general notations, that would be t minus here to some t between t minus and t plus. Well, anyway, so it's a complete analog of the Fourier transform, only we use the solution to our system instead of the exponential function, and we add this weight in the L2, the weight given by the Hamiltonian. And so the branch spaces are Fourier, Weil Fourier images of L2 of H. And moreover, looking a little bit ahead, all so-called regular de Branch spaces appear this way from some canonical systems. So in a sense, there is a one-to-one correspondence between canonical systems and chains of de Branch spaces. All right, so now our goal is to talk about spectral problems for canonical systems. Now, spectral problem, a direct problem, is when you want to find the spectral measure of the system from the system itself. And the inverse spectral problem is when you want to recover the system from its spectral measure. So first of all, let us define the spectral measure for a canonical Hamiltonian system. Now, the notion of a spectral measure of a differential equation appeared before the spectral theorem, which talks about spectral measures of normal operators. So this is an older definition. And let me first give this definition, and then we will discuss the connection with spectral measures for normal operators as we know them in present times. So if you're given a canonical system of this form with some self-adjoint boundary conditions at both endpoints, then you can consider spectral measure of the system, which is the following object. This is a locally finite non-negative scalar measure for which all the de-branch spaces fall isometrically, are embedded isometrically into L2 of mu. So that's one of the definitions of a spectral measure. A quick note here is that under the restriction that the Hamiltonian is locally summable, your spectral measure will always be Poisson finite, which means this property. So to say that all the branch spaces are embedded isometrically into L2 of mu is one of two possible equivalent definitions of the spectral measure. The second definition is that the Fourier Weyl transform extends to a unitary operator from L2 of H to L2 of mu. So what is the connection of these two definitions, which are equivalent, and the spectral measure from the spectral theorem for normal operators? Well, this is something that I already mentioned. If H of t is invertible, we can multiply both sides by H inverse, and then we will have the equation H inverse omega x dot equals to Zx. This will be an eigenvalue equation for a formal operator H inverse omega x dot. And so if H inverse exists, and this could be extended to a true self-adjoint operator, then you can apply the spectral theorem and find its spectral measure, and this will be the same measure as we've defined here. But our definition is slightly more general because we can talk about the spectral measure even if this formal expression with H inverse doesn't exist. So what we are using here is an older definition of a spectral measure for a differential operator, which is of course connected to what we call the spectral measure now. All right. So, well, as we can see from the definition of the Weyl Fourier transform, the branch spaces that appear from a fixed canonical system, they form a chain. They are isometrically embedded into one another, and all are embedded into L2 of mu, where mu is the spectral measure. Of course, in the case when H is the identity matrix, the spectral measure will be the Lebesgue measure, the spaces will be the Pellew-Wiener spaces, and this is the simplest example of such a chain that you can give. So a quick and natural question is whether the spectral measure for a canonical system is unique. And this is a very well-known question in mathematical physics. The case when the spectral measure for a differential operator is unique is called the limit point case, and the case when it's not unique is called the limit circle case. And in this Crane-de branch theory, when you look at a canonical system, it's very easy to distinguish the two cases. Namely, if you calculate the trace of your Hamiltonian and the integral of this trace is finite, then it's a limit circle case. The spectral measure is non-unique. Actually, there's the whole family of spectral measures. Some people in the audience saw this family as a family of Clark measures corresponding to a fixed inner function. But if the integral of the trace is infinite, then it's the so-called limit point case, and then the measure is unique. All right, and as I mentioned before, now we will talk about spectral problems, and the direct spectral problem is to find the spectral measure given the Hamiltonian, and the inverse spectral problem is to find the Hamiltonian given the spectral measure. Now, spectral problems are important in mathematical physics, and they've been studied for about 100 years at least. Maybe the modern history of this question starts with results of Borg and Marchenko in 1950s, who were first to establish the uniqueness of the inverse spectral problem for Schrödinger operators on an interval. So if you're given a spectral measure of a Schrödinger operator on an interval, then there is a unique Schrödinger operator corresponding to that measure. So the theory was later extended to much broader classes of differential operators by Gelfand and Levitan. Still, there are many restrictions on the equations, the potentials, the Hamiltonians, and the spectral measures under which they could prove the uniqueness theorems and some existence theorems and so on. And our goal today is to extend those classical theories to much broader classes of spectral measures and Hamiltonians. We also would like to give some algorithms on how to construct a Hamiltonian when you're given a spectral measure. And as I mentioned at the beginning, this is joint work with Nikolai Makarov. And before I give you some of our results, I need to give a few more definitions. First of all, let's recall the second axiomatic definition of a de branch space and the second axiom in that definition, which said that point evaluations for non-real lambdas must always be bounded linear functionals in the space. As I mentioned, the non-real part of that axiom is not really important. You can quickly extend it to all real lambdas as well. And then your space of entire functions becomes a so-called reproducing kernel Hilbert space, because if point evaluations are bounded linear functionals, then by the representation theorem, there must be a function in the same Hilbert space which realizes that point evaluation. So for each lambda in the complex plane, we must have a function k lambda in the space such that the point evaluation at the point lambda for any function from the space is the inner product with that function k lambda. Just like in most other reproducing kernel Hilbert spaces of analytic functions, you can find the formula for those reproducing kernels. So A and B in this formula are the real and the imaginary parts of our function E, the Hermite-Biller function that generates our space on the real line. So here are the definitions. They're both entire functions which are real on the real line, and they're defined this way. E sharp is once again that Schwartz reflection. E and E sharp are complex conjugates of each other on the real line. So these two functions could be viewed as analogs of sine and cosine for a general Hermite-Biller function. For the main example of an Hermite-Biller function, the exponential function, they will be sine and cosine, and for the general E, they're defined like this. And then this is the formula for the reproducing kernel corresponding to the point lambda. So it turns out that if you know reproducing kernels in your de Branch spaces, which you obtained from the canonical system via this while Fourier transform, or just define them after you found the solutions, you made functions E for each fixed t, and then define them using the first definition of a de Branch space. So you define the spaces and suppose that you found the reproducing kernels as well. So a quick theorem is shows you how to recover the Hamiltonian from the reproducing kernels. Before I formulate this theorem, let's recall that I actually didn't say it, but to simplify my statements, I did say it in one of the first slides. We agreed that we will only consider systems today for which the Hamiltonian has non-zero determinant almost everywhere. And then the next sentence was that in this case, you can renormalize the system with a change of variables so that the determinant is actually 1 almost everywhere. So now let's assume one more restriction. Let's consider only the systems for which the spectral measures are even. Now, all those restrictions together, they're not very important. We can formulate similar results without those restrictions. But with those restrictions, it will allow me to formulate this theorem in an especially simple way. So when the spectral measure of this Hamiltonian system is even, this happens if and only if the Hamiltonian is a diagonal matrix. Moreover, if the determinant is 1, then these two must be reciprocals of each other. And so to recover the whole Hamiltonian, in this case, we will only need to recover one of the functions on the diagonal. And this theorem shows you quickly how to recover that one function if you know the reproducing kernels of your de Branch spaces at 0. Namely, you take the norm squared, its derivative with respect to t times pi, and that will give you h11, and h22 is 1 divided by h11. And since the Hamiltonian is diagonal, this is all that you need. Now, once again, if the Hamiltonian is not diagonal, we have similar formulas for the off-diagonal elements as well, but that would take me perhaps more than a page to formulate the full theorem. So I'm only showing you the simple version. All right, so now that we know how to recover a Hamiltonian from reproducing kernels, let's recall that our main goal is to learn how to solve an inverse spectral problem. So we want to recover the Hamiltonian from the spectral measure. So far, we only know how to recover Hamiltonian from reproducing kernels. So now the question becomes how to recover reproducing kernels from the spectral measure. And for that, we will need a bit more, several more definitions. First of all, let's recall the formula for the classical linear Fourier transform. I'll use this formula with this coefficient in front to make it unitary. And let's recall that the classical Pelle-Wiener spaces are images of L2 on the interval from -a to a under this Fourier transform. An equivalent definition of the Pelle-Wiener space is that it's the space of entire functions of exponential type at most a, which belong to L2 on the real line. And now we need to make a small excursion into harmonic analysis and talk about sampling measures for Pelle-Wiener spaces. We will need this theory to help us solve the inverse spectral problem at the end. So let's recall what is a sampling measure for a Pelle-Wiener space. Now, a positive measure on the real line is sampling if the following inequality holds. If the L2 norm with respect to that measure is equivalent to the norm in the Pelle-Wiener space, which is, by the way, just the L2 norm with respect to the Lebesgue measure on the real line. Now, describing sampling measures for Pelle-Wiener spaces is a difficult problem. It's equivalent to describing sampling sequences for Pelle-Wiener spaces, and a sampling sequence is a sequence of points on the real line such that the little L2 norm of the values of a function at those points is equivalent to the Pelle-Wiener norm of that function for every function from the Pelle-Wiener space. Now, both problems are equivalent to the problem of description of Fourier frames or frames of complex exponentials in L2 on this interval. And that problem was posed by Daphne and Schaefer in 1952. Then there was a very nice sufficient condition by Landau. And then there was an annals paper by Ortega, Cerda, and Sape 20 years ago, which gave a description of sampling sequences and sampling measures in terms of existence of certain Hermite-Biller functions. By the way, this paper is a very nice example of an application of the theory of de Branche spaces, because they used some theorems from de Branche's book to give that description. So what I wanted to say here is that description of sampling measures for Pelle-Wiener spaces is a difficult problem, but the problem becomes much simpler if you want to describe measures such that the measure is sampling for every Pelle-Wiener space. So to describe measures which are sampling for a fixed Pelle-Wiener space is difficult, but describing measures which are sampling for all Pelle-Wiener spaces is much simpler. And fortunately for us, those are the measures that we will need in our inverse spectral problem. So I see that I am almost out of time, so this will be our last slide for today. And this is a statement, a theorem that describes Pelle-Wiener measures, which by definition are measures such that they're sampling for every Pelle-Wiener space. Now, the constants in that inequality will, of course, depend on A, but by the definition, the measure is Pelley-Wiener if those constants, these two constants, exist for every A. And we will discuss this statement next time, and we will discuss how this statement can be used to solve the inverse spectral problem. But I think I should stop for now. Thank you.
Thank you, Alex. Thank you for a wonderful talk. Questions, suggestions, comments?
Yes. I have a question.
Oh, please.
So you said that in the limit circle case, in the limit point case, there is a one-to-one correspondence between spectral measure and the Hamiltonian.
In some sense, yes.
In some sense. Oh, okay. So if we approach this through m functions, there is an extra linear term in the representation, az plus b plus Schwarz integral of the measure. And in this setting, do we assume b as part of the measure as point mass of infinity, or this linear term just disappears?
In the settings of canonical systems, the spectral measure will not have a point mass at infinity. So the theory says that you consider a canonical system with locally summable Hamiltonian on the half line, and you, let's say, trace normalize it. So normalize it so that the trace of the Hamiltonian is equal to 1 almost everywhere. Then there is a one-to-one correspondence between such trace normalized locally summable systems and Poisson finite measures on the real line without point masses at infinity. So that's roughly the statement. Yeah.
Thank you.
More questions or comments?
Yes, I have two questions. So the first one is a basic one. In your second axiomatic definition, you said that the E is not known, but what's the information given by the proof of the theorem?
Yes, so it's still a bit implicit. So you first use the second axiom, which says that the point evaluations are bounded. And that means that there exist reproducing kernels. And then you try to extract E from the reproducing kernels. Remember, we had a formula for the reproducing kernel, which has those A's and B's. If you know those A's and B's, then E is A plus IB. So if you look at, for instance, the Makin book, as I mentioned, they have a, so the book is called Gaussian Processes and so on and so forth. I don't remember the exact title, but they give a formula for E in terms of the reproducing kernels Ki. So they take the reproducing kernel at the point I and give the formula for E in terms of it. But of course, the reproducing kernel exists because the point evaluation is bounded, but you don't really have it. So it's not an explicit formula for E, but the existence result.
Okay, thank you. And my second question is, do we have an analog of the Poisson formula for your Fourier transform?
The Poisson for, oh, you mean that the Fourier transform of a counting measure is again a counting measure? I guess there should be. But it's an interesting question. I haven't thought about it. There should be an analog of it, of course. Yeah.
Okay, thank you.
More questions or comments? If not, let's thank Alex again.